Hey, what's up, everybody? Today is March 21st, 2025, another day for Leetcode. We're going to get right into it and get our practice underway. Alright, let's go ahead and check out the problem of the day. 2685, count the number of complete components. Oh, I've done this before. You are given an integer n. There is an undirected graph with n vertices, numbered from 0 to n minus 1. You are given a 2D integer array edges, where edges I equals a I b. To notice there exists an undirected edge connecting vertices AI and BI. Return the number of complete connected components of the graph. A connected component is a subgraph of a graph in which there exists a path between any two vertices, and no vertex of the subgraph shares an edge with a vertex outside of the subgraph. How can it share an edge with something outside of the subgraph? A connected component is said to be complete if there exists an edge between every pair of its vertices. Okay. So every node needs to have n minus 1 edges. And then you have level. I could probably do a breadth first search and a count. We'll try that out first. So first we need an adjacency list. So edges A to B. Yeah. So this is going to be in. I guess I could do this. I don't think I need the indexing. Um, Okay. Yeah, if it's new, we can do this. Q, get push 0. Scene I like to put up here. Scene I goes 1. While not q.empty. And then we're going to go ahead and go into a breadth first search to do the count, right? So all the counts need to be in -1. So this is 3. So all the edges in here need to have 2 edges. Okay. Oh, I messed up my glasses. Give me 1 second. Luckily, I'm getting new glasses soon. A couple weeks. And then I want to use these 3D printed nose pads I modeled. Okay, so how do we count, or how do we want to keep track of all the edges in this subgraph? It's the first thing we have to ask, right? Because we don't know the size, so we need a count. So we could do a level order, but that wouldn't work. Okay. We could do an unordered set, right? That would give me the subgraph. So if I did something like or I can list in nodes for local, right? Vector int subgraph, right? And then I can go in 0. And then I can just mark the scene ones. Okay. So we'll go. First, we need the size. Well, actually, we can get the size from the subgraph. Yeah. So we'll go while. So we don't need a level order. So while front q.pop. We already marked the one that we had in here as seen for I. But then we also need to mark the subgraph I equals 1, right? So this is the non-local. This is the local. Then when we go to check its neighbors, for auto if scene child continue child 1 subgraph graph 1. And then we just push child. All right, so do, and then we could have a result. And then we say, or then we go through the subgraph. Int edges, no. Int nodes equal okay. So we'll then go through and we'll say, because we have the adjacency list, which means this will point to this and this. We're just looking for the size. So we'll say bool valid equals true for auto subgraph say if no. If the node, I'm sorry, I did this wrong. If edges does not equal adjacency list I dot size. Oh wait, hold on. We're not going through. We're going through the subgraph, right? So if subgraph I and edges does not equal this, then continue. Or no, then this is invalid. If subgraph I, which means that we now saying that this is equal, or no, if we just say else if subgraph I, if edge is equal, then do nothing. Yeah, that's all you have to do, right? So if it's in a subgraph and the size is not equal to edges, then return valid. If valid result plus plus. Right. And then we should be able to just return result once the breadth first search is done. Let's see, this needs to start at 0. Well, let's see, first iterator, last iterator, and initial. Initial. Okay, 2, 3. One node has no things, so should be 3, right? This is node 5. first off, this is wrong. It should be J. Okay. Okay, so 0 is here. 3 is here. 3 to 4. Wait, why is 4 popping up? It's within the subgraph. I would have marked 3 as seen. Subgraph is seen. But right here, the childs are seen for the adjacency list. So 4 should have been seen. And then we have 5. You mark 5. It's 0. You mark the subgraph as 5. Q dot push I. 0, 3, 5. That's more accurate. Okay, I don't see why this wouldn't work. Yeah, that works. Okay, well, that's the problem for the day. Yeah. Basically, to explain what I did, is I created an adjacency list. I kept track of the values that I've seen, or the nodes that I've been seeing. I went through and iterated through every node. And then anytime I've seen something I've already seen, I'm going to just continue. And I'll immediately mark the first, or the node that I'm on. So I don't I'm not going back over things again. Then I'm going to keep track of what I would like to call a subgraph. So we have the non-local and the local graphs. And in the local graph, so if we have, say, this, right? This 3 disjoint graph right here is going to be part of what I'd call the subgraph for the BFS. I would then mark the subgraphs that I find. So we mark what we've seen. We count the number of nodes in the subgraph, and then make sure that whatever's in the subgraph has the correct number of edges for a complete. It has a number, it's complete components, right? And then if we ensure that it has complete components, then we're just going to add to the value because this is a complete connected component of the graph. That's it. That's my solution. Anyway, thank you for joining me today. I hope you have a wonderful evening. Have a good evening. Again, peace.